Welcome to this explainer. Today, we're bridging the gap between basic desktop extrusion and advanced industrial additive manufacturing. We're going to take a comprehensive layer-by-layer journey through the source material on the entire 3D printing ecosystem. Let's dive right in and explore how hardware, software, and physical thermodynamics all intersect to turn our digital ideas into physical reality.
Here's our roadmap for today's journey. First, the 3D printing revolution. Second, upgrading the printer's brain. Third, perfecting the first layer. Fourth, the need for speed. And finally, designing for 3D printing. Let's get started.
Section 1. The 3D printing revolution.
Additive manufacturing isn't actually as new as some folks might think. It's fascinating to see that the groundwork was laid way back in the 1980s, with the very first stereolithography patents filed by Dr. Hideo Kodama and Chuck Hull. But the real explosion, that hit in the 2000s, thanks to open-source initiatives like the RepRap project, which literally aimed to create a printer that could print its own parts. Access to this tech was completely democratized. Now, in the 2010s and 2020s, the application has just skyrocketed. We're seeing 3D printing used to create everything from highly personalized medical implants to ultra-lightweight aerospace components. Now, while there are dozens of highly specialized methods out there today, the industry's foundation really rests on three core technologies. First up, there's good old FFF, or FDM, which is all about melting and extruding plastic filament layer by layer. Next is SLA. This method uses UV lasers to cure liquid photopolymer resin, giving you that mind-blowing, hyper-realistic detail. And finally, we have SLS. This uses high-powered lasers to fuse polymer powders. The amazing thing about SLS is that it creates fully functional, incredibly durable parts without needing any generated support structures whatsoever.
Section 2. Upgrading the printer's brain.
Moving from the hardware basics, it's really interesting to contrast the two heavyweights in firmware today, Marlin and Klipper. Marlin is your reliable, rock-solid standard. It runs locally, directly on the printer's mainboard, offering incredible stability. It's especially great for multifunction machines. For example, the Snapmaker Artisan uses Marlin because it needs absolute, fail-safe stability to switch between 3D printing, CNC carving, and laser engraving. Then you have Klipper, the absolute speed demon of the bunch. Klipper actually outsources all the heavy mathematical processing to a secondary computer, like a Raspberry Pi. This massive boost in computing power unlocks advanced features like input shaping, which literally predicts and cancels out machine vibrations before they even happen. High-speed machines, like the Snapmaker U1, heavily leverage Klipper to print flawlessly at blazing speeds.
Section 3. Perfecting the first layer.
We've all been there, right? You walk away from a printer feeling great, only to return hours later to a giant ball of plastic spaghetti. So why exactly do prints fail on layer 1? The vast majority of the time, an unleveled bed is the ultimate culprit. Even a tiny variation causes first-layer inconsistencies, severe thermal warping, and total print failure. Ultimately, it just wastes your machine time and your expensive filament. This is exactly where Auto Bed Leveling, or ABL, swoops in to save the day. ABL solves this dilemma by using a tiny sensor attached to the printhead to digitally feel the topography of your build plate. It takes micro measurements at multiple points to create a highly accurate digital mesh. Then, while the printer is actually running, the firmware uses this mesh to automatically adjust the Z-axis height in real time, microscopically raising and lowering the nozzle so it maintains a perfectly consistent distance from the bed. Now, you've got a few distinct sensor types to choose from to pull this off. The AntClab's BL Touch, for example, uses a Hall effect magnetic sensor and physically taps the bed with a pin. That means it works on absolutely any surface. Glass, metal, plastic, you name it. Then you have inductive sensors, like the Prusa SuperPinda. These are non-contact and incredibly reliable, but they strictly require a metal bed so they can detect the magnetic field. Finally, we have microswitches, like the Euclid probe, which physically click against the bed and offer just unparalleled mechanical precision. Honestly, choosing the right sensor completely dictates what kind of build surfaces you can experiment with.
Section 4. The need for speed.
Okay, once your brain is upgraded and your first layer is flawless, the natural next step is wanting to print faster. But the source material highlights a massive physical bottleneck here: volumetric flow rate. This is the absolute maximum volume of plastic that your specific hot end and extruder can successfully melt and push through the nozzle per second. It's measured in cubic millimeters per second. Why is this so critical? Because you simply cannot outrun the thermodynamics of your hot end. You can use a very simple formula, speed equals your volumetric flow divided by your layer height divided by your line width, to mathematically determine your machine's maximum safe print speed.
Let's put a real-world number on this to show you what I mean. 24. A standard E3D V6 hot end, which is incredibly common, caps out at a volumetric flow rate of around 11 cubic millimeters per second. But by upgrading to a high-flow hot end like the Dragon HF, you push that physical limit all the way up to 24. That single hardware swap allows for dramatically faster cycle times, simply because your machine can physically melt plastic more than twice as fast.
So how do you find the absolute limit of the hot end sitting on your desk right now? Tuning your specific flow rate limit using Ellis's method is brilliant, and it's actually super straightforward. First, you heat your hot end to your standard printing temp. Next, grab a piece of tape or a marker and mark exactly 100 millimeters of filament right before it enters your extruder. Then command the printer to extrude at increasing speeds. You just keep measuring to see if it actually pulled the full 100 millimeters in. Eventually, the extruder is going to start clicking and skipping, and you'll hit what's called flow drop-off. Once you hit that thermodynamic wall, you take your maximum successful speed, plug it right back into that formula, and boom, you have mathematically defined the absolute speed limit of your 3D printer.
Section 5. Designing for 3D printing.
Having a perfectly tuned machine is fantastic, but it's totally useless if your digital blueprint is flawed. This quote from Rapid Direct really captures a massive mindset shift. It says that in an industrial ecosystem, engineers have to completely abandon consumer-level generalities and strictly design around process-specific thermodynamic boundaries. You can't just tweak an infill slider in your Flicer anymore. You have to deliberately define your part's geometry from the ground up.
Take mechanical tolerances, for example. To ensure multi-part assemblies actually snap together, your clearances have to be adjusted based on the specific printing tech. SLA resin printing is hyper-precise. It can handle extremely tight press-fit tolerances of just 0.1 to 0.15 millimeters. But listen, if you try to use those same tiny digital clearances on an FDM extrusion printer, your parts will literally fuse together into a solid block. FDM requires up to 0.35 millimeters of clearance just to compensate for heavy layer lines and localized thermal warping. You have to design for this specific machine.
Building on that, there are some pretty hardcore structural rules for design for manufacturing, or DFM, that engineers need to follow. First up, FDM walls absolutely must be exact integer multiples of your nozzle diameter. So if you're running a 0.4 millimeter nozzle, your walls should be 0.8, 1.2, or 1.6 millimeters thick. If you design a 1.0 millimeter wall, the printer is forced to do thousands of tiny micro-vibrational gap-filling maneuvers in the center. Yeah, that completely ruins the structural integrity and balloons your print time. Next, keep adjacent walls within a 60% thickness ratio of each other. Anything thicker traps heat in the core and causes massive thermal warping. Third, for hollow SLS powder prints, always include at least 2 3mm drainage holes so you can extract the trapped unsintered powder. And finally, to combat the dreaded elephant's foot, where the bottom layer squishes outward because of the heated bed, just integrate a tiny 45-degree chamfer along the bottom edge of your CAD model. It works wonders.
3D printing is such a beautifully complex ecosystem. Hardware mechanics, firmware brains, and strict geometric design all have to converge perfectly. Mastering this interplay is what truly empowers you to bypass all those frustrated failed first layers and really start outpacing traditional manufacturing. So knowing all these strict industrial boundaries and thermodynamic limits, how are you going to rethink your next CAD geometry or firmware upgrade to achieve that perfect print? Thank you so much for joining me on this explainer, and happy printing.